Good day and welcome back. In today's video we will continue on this discussion of differentiation by beginning our discussion of the chain rule for functions of several variables. To get started, let's go ahead and just remind ourselves of how that chain rule works in Calculus 1. The chain rule is intended for differentiating functions that are compositions. Here if y is equal to f of g of t, and that of is really indicating that we have a composition. What we learn in Calculus 1 is that this is equal to the derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. Now there is another way that is completely acceptable and equivalent for us to think about this. We could think of y as being some function of x, with the x being some function of t. Then in this case, we could write this as dy dt, the quantity we want to find, is dy dx multiplied by dx dt, which is more similar to how we are going to write the chain rule in this Calc 3 version. And I do want to note that implicit to this notation, when we have this dy dx, you're really substituting in x equals g of t, so that all of our quantities do end up depending upon t, and this x equals g of t we substitute in is really evaluating at the inside function. But it is important to point out that is implicit to the notation. We will have two versions of the chain rule. Starting with version 1 will give us a little bit of intuition and is a good starting point. If we have a function of two variables, so we think z is a function of x and a function of y, with both x and y being functions of t. And for today's discussion, we assume everything is perfectly differentiable. So I'm intuitively thinking, and I'm going to draw diagrams later on, so we'll start now, that we have z, or f, which depends upon x and y, and x depends upon t. So as we progress downward through this tree diagram, it's showing you what a function or variable depends upon. Z depends on x and y both individually depend upon t. So note z is only a function of t when we plug in those values. So z in this case is only a function of t, which means it's not a partial derivative, it's an ordinary derivative, i.e. what we've dealt with many times in the past. And the version of the chain rules, we take the derivative of f with respect to x, and that is a partial derivative, and then we multiply by dx dt. Similarly, we have to add on to this the partial of f with respect to y times dy dt. And in a sense, we can see this in our diagram that we have to the right, where we think each of these terms in the chain rule which we are adding up is going to correspond in a sense to going down a branch of this tree diagram. And we'll revisit that a bit more carefully with version 2. For now, what I would like to do is look at an example. For the function given by x squared plus y squared plus xy, where x is sine of t and y equals e of t, find the derivative dz dt. And I do want to note there's two perfectly good ways to go about this. We could look at x equals sine t, and we could replace each of the x's with sine. Because y is equal to e of t, we could replace each y with an e to the t. And when you've done so, you've really turned this into a familiar Calculus 1 problem. But instead of approaching it from that Calculus 1 perspective, we are going to use the chain rule as described above. So I'm going to begin by just simply writing this out. dz dt is equal to the partial derivative of z with respect to x times dx dt, plus the partial derivative of z with respect to y times dy dt. And in case you're wondering, it's worth noting that we could do similar kind of computations if z happened to be a function of more than two variables. Each variable would really just kind of indicate an additional term we would need to add. So let's go ahead and substitute in what these partials are. So the partial of z with respect to x, just investigating what we see above, we treat the y's as constant, so 2x plus y, times dx dt. The derivative of sine is cosine, plus the partial of z with respect to y, so 2y plus x, multiplied by dy dt, e to the t. Now remember we mentioned that z is a function only of the variable t, so dz dt should only depend upon the variable t. So what we need to do, similar to our observation and note in that original Calc 1 formula, is we need in terms of t. That is, we need to substitute x equals sine of t and y equals e to the t. And performing these substitutions will give us 2 times sine plus e to the t times cosine plus 2e to the t plus sine of t multiplied by e to the t. And as usual, there's some number of combinations or simplifications one might want to do here. I strongly encourage you to leave it exactly in this given form. So let's finish this first version of the chain rule by looking at one additional example. So consider the following problem. The radius of a right circular cone is increasing at a certain rate while its height is decreasing at another rate. At what rate is the volume of the cone changing when the radius is 120 inches and the height is 140 inches? And note, this last sentence is telling us precisely what we would like to find. What we would like to do is find the rate of change of the volume, which is a derivative, dv dt, precisely when the radius is 120 and the height is 140. Some other key bits of information hinge upon the values 1.8 and 2.5. So let's just note what those quantities are as well. The radius of a right circular cone is increasing at a rate of 1.8. So a rate of change is a derivative. dr dt equals 1.8 inches per second. Similarly, its height decreases at 2.5 inches per second. So dh dt involves at 2.5 inches per second. But we have to be careful. Decreasing indicates a negative rate of change. So this should be minus 2.5 inches per second. And just be very careful with that minus. A common mistake is to omit it. So now that we've identified what we know and what we want to find, let's see if we can go ahead and do that. So the volume of a right circular cone is something that's somewhat familiar. We might not use it all that frequently, but we have certainly encountered it. It is 1/3 of the volume of the cylinder which it lies in. So 1/3 pi r squared h. And if you're looking at something like this and saying, well, I would not have remembered it, now that we've seen it, it does become more familiar if we do encounter it again. So dv dt, using the chain rule above, and if we want to think about this in terms of a diagram, v depends upon r and h, while r and h both depend upon t. So dv dt, using the chain rule, would be the partial derivative of v with respect to r multiplied by dr dt plus the partial derivative of v with respect to h times dh dt. And it's worth noting that if you prefer, you could also use the partial notation, but it's just as convenient, and more so convenient here, to write v sub h. Now, substituting in the formulas, the partial derivative of v with respect to r would be 2/3 pi r h dr dt, plus v sub h would be 1/3 pi r squared, and this is multiplied by dh dt. And we are now ready to determine the desired rate of change. So dv dt when r is 120 and h is equal to 140 is as follows. And before I write anything down, I want to note that including this notation is a key step in the problem. A common mistake is to simply, just take what's in the previous step, set it equal to what you get when you substitute in the values. The problem with that is one is representing a function, while the other one is representing a concrete numeric value. So what we see above with what we're about to write down is not equal because it's an evaluation of that above quantity. So be warned. Substituting in our values, we have 2/3 pi times r times h, and we've indicated above that dr dt is 1.8 inches per second, plus 1/3 pi r squared multiplied by dh dt, which is minus 2.5. And if we were to combine all of these numbers together using a calculator is more than okay, what we would end up with is 8,160 pi. In terms of units, I recommend not overthinking this. Just note, what are we calculating? The rate of change of a volume. So the units associated with volume would be inches cubed with respect to time, and the time in this problem has been indicated as seconds. So this completes a discussion of the first part of the chain rule. In our next video, we will move on to version 2 of the chain rule. So stay tuned and take care.